So I wanted to start this week by practicing a bit of the things you learned last week. Last week the topic was gravity. So the main thing to know about gravity is the formula for the force of gravity. And the force of gravity equals to mg. So that's an object's mass multiplied by the gravitational field strength. That'll give you how many newtons the force of gravity is. And the gravitational field strength for Earth is 9.8 newtons per kilogram. That number is for the Earth, and the number is different for different planets and for the moon. So that's the main thing about the force of gravity. Also, you want to know that the force of gravity is down. Okay, every question near the surface of the Earth, when you draw a free body diagram, the force of gravity should point straight down. So last week I got you to learn about some elevator problems and maybe did a few other problems, the problem set. Here's a couple of more problems related to the force of gravity. So this first one here is a block on a block, basically. So we have a 4 kilogram block rests on top of a 10 kilogram block, which rests on the floor. Draw a free body diagram for each block and determine the value of each individual force. Okay, so basically this question is asking us to break down both of these blocks and to figure out how many newtons are being applied on these blocks by every single kind of force acting on them. So I'm going to split my page in half, and on the one side I'll talk about the red block, which is 4 kilograms. And on the other side I'll talk about the blue block, which is 10 kilograms. Okay, so in terms of the red block has a force of gravity acting downwards on it. And it has an upwards force, and that's the force upwards from the blue block. So we can call that a normal force because the blue block is technically a surface. However, I'm actually going to call it an applied force. I'm calling it that because I'm going to reserve the word normal force for the floor pushing up on the blue block. Okay, so just so I don't throw out the term normal force too many times, that can get confusing, I'll just call this one the applied force. All right, and since everything is at rest, the forces have to be balanced. That's Newton's first law. Okay, that's Newton's first law. So that means that these two forces are equal, and I can calculate them. The force of gravity, as I just showed on the first slide, is equal to m times g. That's the formula for the force of gravity. So for this 4 kilogram block, it's 4.0 times 9.8, and that is 39.2 newtons. So that'll be to two significant figures. I'll just underline 2 digits there. All right, and since the forces are balanced, because it's at rest, that means the applied force must be equal to that. So the applied force must also equal 39.2 newtons. All right, so that's the red block. Now the blue block is a little bit more complicated. So the blue block has its own force of gravity, down. And it's got sorry, I'm just gonna redraw this here. I realized that I was going to run out of space. All right, so let me try this again. We're going to have a blue block with the force of gravity. Now, the applied force of 39.2 newtons, that was the blue block pushing up on the red block. But due to Newton's third law, the red block's going to apply an equal and opposite reaction force downwards on the blue block. Okay, so I have to actually include the applied force downwards. That's the red block pushing down on the blue block. And it's going to be 39.2 newtons. Okay, so I actually have two downwards forces on this blue block. And then I'm going to have the normal force from the ground, which I'm going to draw quite large. Okay, the blue block is at rest as well. That means all the forces have to be balanced. And since I have two downward forces, my upward force has to be equal to the two of them combined. Okay, so what I'm trying to say is that the normal force in magnitude must balance out the force of gravity plus the downward applied force. Okay, now I can calculate each of them. So the force of gravity will be mg. So this block is 10 kilograms. So 10 times 9.8, which will give me 98 newtons. The applied force is equal. Okay, it's equal to the applied force from the previous side because of Newton's third law. I'll just round it to the correct number of sig figs, which is 2 sig figs, so 39 newtons. So therefore, knowing those two numbers, I can now calculate my normal force because it has to equal the two of them combined. That'll be 137 newtons. And since we're adding, we round to the appropriate decimal place. So 98 and 39 are both rounded to the ones column, so my answer should be rounded to the ones column. So that's how you do this question here. And now I have this last question. This question is a challenging one. And you can know it's a challenging one because it's got this indication here of a level 3 problem. So this is taken from a physics textbook that likes to divide its problems into levels 1, 2, and 3, with level 3 being the most difficult one. Okay, so I'm going to take a look at this one here, help you work through it. It says a person jumps from the roof of a house 3.9 meters high. When he strikes the ground below, he bends his knees so that his torso decelerates over an approximate distance of 0.70 meters. If the mass of his torso, excluding legs, is 42 kilograms, find A, his velocity just before his feet strike the ground, and B, the average force exerted on his torso by his legs during the deceleration. So that's a lot to take in. That's a lot of words. You got to visualize what's going on. He's basically jumping off a roof, landing on the ground. And in order to soften his landing, he bends his knees. Okay, every time you jump and you land, you should always bend your knees as you're landing. That'll help soften the landing. If you don't, it could hurt quite a bit. All right, so part A, I'll start with part A. This is actually going back to unit 1. Okay, this is going back to unit 1. We're going to find his velocity just before his feet strike the ground. So we're going to assume that the initial velocity is at rest. Okay, so it says he jumps off a roof, but I'm just gonna say he's just gonna step off the roof so that he's barely moving when he gets off that roof there. So we have a starting velocity of 0. The person's gonna fall down to the ground, and the displacement, it says, is 3.9 meters. Okay, that would be down. And let's not forget that we know the acceleration when he's falling down. The acceleration is 9.8 meters per second squared down. And we're asked to find the velocity just before he hits the ground, which will be v2 as a question mark. So then we sift through our Unit 1 formulas. They were posted at the front of the classroom, but you guys will have to look through your notes and try to find the formulas there. And the formula you will choose is the last one, which I'm writing out here. I'm going to cross out the v1 squared because the value is 0. And then I have to find v2. So all I have to do is square root both sides, and that'll do it. So I'll fill in the values. 2, 9.8, 3.9. Okay, and then I gotta find that out. So I'm gonna go grab my calculator here. Okay, and the calculator is giving me 8.743. That'll be meters per second down. And for sig figs, I have to keep 2. And I just kept 2 extra ones so that my answer can be more accurate for part B. All right, part B. So part B asks us to find the average force exerted on his torso by his legs during the deceleration. So I have to find the force. I'm going to draw a free body diagram of the torso. Okay, because we're talking about the torso here. So the torso is 42 kilograms. I'll just write that there. And so it's got a force of gravity acting down on the torso. And what is holding the torso up? Well, it's the person's legs. Okay, it says by his legs. So there's an upwards force, which I'll just call an applied force. That's the force of the person's legs on his torso. And these two forces are not equal, okay, because it's not at rest, it's not at constant velocity. It says that there's a deceleration, so the person's slowing down. All right. How do I find out this applied force? I can find out the force of gravity easily enough. That'll be 42 times 9.8. So the calculator gives me 411.6. Okay, but how do I find out the amount of upwards force? Well, what you're going to need to do is find out the net force, basically. Okay, if you can find out the net force, then you can figure out how much the applied force has to be. However, in order to find the net force, you would use Newton's second law to do that. You'd have to know the acceleration. And the acceleration is something you have to calculate. Okay, we have to calculate the acceleration first. So I'm going to make a little heading here. Now the book, or this question, calls it deceleration. I'm just calling it acceleration. So the starting velocity, this person's falling down, and when they hit the ground with the velocity we calculated in part A. Okay, so we're transferring the value from part A. Now V2, at the end of the jump, he's going to end up at rest. Okay, so after he's bent his knees and slowed down, he's completely stopped, so V2 is 0. The displacement is how much he bends his knees by, which is 0.70 meters down, okay, because his body is still dropping as he bends his knees. And we have to find the acceleration. Okay, so we're still using Unit 1 stuff. Actually, we use the same formula. This time V2 is 0. And we're solving for acceleration. So to get acceleration, I'm going to subtract V1 squared, both sides, as well as divide by 2 displacement on both sides. Okay, that'll get me the acceleration. So that'll be negative 8.743 squared over 2, 0.7. And that gives me 54.6 meters per second squared down. Okay, and my answer is negative. Okay, my answer is negative down. So that's really the same as positive up. So the acceleration is up. And that's why I drew my applied force upwards larger than the force of gravity. Okay, now I'm going to use this, running out of space here. I'm going to use the middle. I'm going to use this acceleration value in Newton's second law. F net equals ma. Okay, so the mass is 42. The acceleration is what I just got. So if I multiply those together, that gives me 2,293 newtons up. And that's the net force. That's the net force. So how much is the applied force? That's what the question is. Okay, so the applied force, take away 411 for the force of gravity, has got to equal my 2,293. Okay, so the applied force magnitude minus the force of gravity magnitude has to equal 2,293. So the applied force will equal to 2,293 plus the force of gravity, which is 411.6. So I will add those two, giving me 2,705 newtons. Now in terms of sig figs, if I go all the way back up to Newton's second law here, that needed to be rounded to 2 sig figs. So then when I now add, I have to go to the hundreds place. So this will be 2.7 times 10 cubed newtons. All right, so that's a really long one. It's quite difficult. But that's why it's a level 3 question in this textbook.